All right, so I'm going to go ahead and start my exam 2, or final exam, the cooling tower problem. So first I just started off by drawing the cooling tower that has a length of 10 meters and an area of 100 meters squared. I'm going to start off by saying that this direction I'm going to call the positive z direction, so down is positive z, because that is the direction that the water moves through the cooling tower. And so that's why I'm going to have that way be positive. So like I just said, the water comes in through the top and goes out the bottom. And we know from the problem statement that the temperature of the water comes in at 70 degrees Celsius, and it comes in at a mass flow rate of 50 kilogram per second. And we do not know the temperature at which the water comes out or the flow rate which it comes out. The other thing is we know the air comes in through the bottom and comes out the top. We know that the air comes in at 5 meters per second. We do not know the mole fraction, and we do not know the temperature. At the top, though, we know that the temperature of the air that leaves is 40 degrees Celsius. And again, we do not know the mole fraction of the water vapor in the air. Some knowns that we have given in the problem is the heat transfer coefficient, which is equal to 10 watts per meters squared times Kelvin, and the Lewis number is 1. We also know the equation for Nusselt number, which is equal to 0.6 Reynolds number to the 1/2 times the Prandtl number to the 1/3. And that's our big key equation for this problem. So jumping right in, we're going to solve for a couple things that we can use later on. So the first is we know that the water-air contact created from the slats is going to be 5 meters squared per meter cubed. So then that means the total contact area is going to be equal to the total area times the length times that contact area due to the slats. So that's 100 meters squared, as we said earlier, 10 meters, and then that 5 meters squared per meters cubed. And that's going to be equal to 5,000 meters squared per meters cubed as the total contact area. Next, I'm going to solve for the superficial mass flow rate of the liquid water that we're going to represent with G and L because it is liquid water. So GL is going to be equal to that mass flow rate, which is that 50 kilograms per second that I stated earlier. And superficial mass flow rate is a per area basis, so we're just going to divide that by the area, which is 100 meters squared, as we said earlier. And that is going to be 0.5 kilogram per meters squared seconds. Next, we're going to do the volumetric flow rate of the air, represent that by VA, and that's going to be found by taking the velocity of the air going in, which is that 5 meters per second, and then multiplying that by the area. And so that's 5 meters per second times 100 meters squared. So our volumetric flow rate of the air is 500 meters cubed per second. So now that we have a couple things started, we're going to go ahead and start working on problem number 1. And we're going to start with the water differential equation. We are going to start with an energy balance because we know that the energy change in the stream comes about because of a temperature change. So that's why we're using a energy balance to represent what we're doing. So we're going to start with the heat capacity of water, and that is in joules per kilogram Kelvin. And we're going to go ahead and multiply that by the flow rate given in the problem, which is the mass flow rate per area that we solved for right up here, this GL, times the area. And so that really, when you look at it, this is just the flow rate given in the problem, which is just that 50, I believe, that 50 kilograms per second. But since we solved for GL, you can just multiply it back against the area and get the flow rate that was given in the problem. Next, we're going to multiply that all by the enthalpy change, which is just the change in the temperature of the water. And that is going to be equal to the cross-sectional area times dz, which is the change in position, and that's just going to be equal to the volume of this cooling tower. And then we need to take into account for the slats. And so then when you look at this, you got your volume, and then this whole thing, though, is going to be meters squared because you're multiplying volume by the slats. Now, we're going to multiply this by, because the amount of mass transfer depends on the difference in concentration, we're going to multiply it by that difference in concentration to some degree. So we're going to start by our proportionality factor, which is our Kc, multiplying that by our heat of vaporization, which is represented by lambda. That's the heat of vaporization of water from a liquid to a vapor, and that is just a literature value. And then this is really important, is this negative sign here, and that negative sign is negative because the temperature of the water decreases as it goes down the cooling tower, so we need to have that negative in there so we have the correct sign for this part of the equation. And then, like I said, because the amount of mass transfer depends on the difference in concentration, we're going to write in that difference in concentration, which is the concentration of the water at the surface times the bulk concentration of the water. And this whole section right here of this proportionality factor and the difference in concentration is going to be the mass transfer. And that's in moles per meter squared. Next, we know that the air transfers heat, and the rate of heat transfer from the air to the surface of the water is the temperature difference. So again, we're just going to write the temperature of the air minus the temperature of the water. And then we are going to multiply that by its own proportionality factor, which in this case is the convective heat transfer coefficient. And then we are going to add that to this term over here because air temperature increases. So this needs to be positive, unlike the other one, which needs to be negative. So there we have our water differential equation, which is really just an energy balance. Clean this up a little bit, get rid of some of my unnecessary marks. And moving on. So next we need to start the air differential equation, but we first need to address enthalpy. Because this is a steady state, we know that the difference in enthalpy, we know that the difference in enthalpy will be constant, so its derivative will be 0 because it's steady state, the net enthalpy. So from the problem, we got our enthalpy of, I'm actually going to color code, enthalpy of water going in, enthalpy of air going this way, and then same down here. So at the top, we have HW minus HA, and at the bottom, we have HW minus HA. So that means that the derivative, like we said, the derivative of the difference, the net enthalpy, is going to be 0 because it is a steady state. So rewriting that, just copying it down here so I can see it, we can say that the derivative of the enthalpy of the water is equal to the derivative of the enthalpy of the air. Another thing we can go ahead and say is that the gas flow rate is going to be equal to the flow rate of the air and the flow rate of the liquid water, because the gas it does have water in it. It is not just straight air, which is why we can't represent it by just GA. It's just going to be big G. And then we can also then use this fact right here, that the derivative of the enthalpy of the air is just the flow rate of the gas, which is the water and the air, on a per area basis. And so we're going to just go ahead and write that down. So that's equal to that. So G. Next, we're going to multiply it again by the area, so then it's not a per area basis anymore. It is just a plain flow rate. Multiply it this similar to above, multiply by the heat capacity of the air. Got the P. And then multiply it by the change in temperature of the air, because as we said earlier, that is what's causing that energy change, is that temperature change. And this other side of the equation is exactly the same as above, so exactly the same as this whole thing. But so we got A, little a times big A, dz. Negative again because of that water cooling. Concentration difference, interface to bulk of the water, plus heat transfer coefficient, the change in temperature from the air to the water. All right, so now we've got our two big equations. I'm going to box those so I can find them at a later point, because this is getting kind of long. Oops, that's ugly. That's okay. All right, moving on. Just gonna start getting some more equations so we can do the last bit, which is the relationship of the mole fraction and finding that differential equation. So we know that the total mass flow rate of the air going in, which is GA, times the area, since that's just the mass flow rate, is equal to the density times the volumetric flow rate. So you got density times Q. This Q is in kilograms per second, and density is in kilograms per meters cubed. And then that statement is equal to again, the density times the volumetric flow rate, but rewritten. We know that density is equal to pressure times average molecular weight over the gas constant times temperature. And the volumetric flow rate is equal to velocity times the area. And this velocity is that 5 meters per second that we had earlier, given in the problem statement. Looking at this, you see that the areas cancel out. So you're left with GA, which is that total mass flow rate of the air going in, is equal to the pressure times the molecular average molecular weight over the gas constant times temperature of the feed times the velocity, which is that 5 meters per second that we know. We can then break this down a little bit more because average molecular weight is equal to the flow rate of the water vapor plus the flow rate of the air over flow rate of the water vapor over the mass of the molecular weight of the water vapor plus the flow rate of the air over the molecular weight of the air. And that's equal to M average. So then now knowing that, we can rewrite the so then moving forward, we need to address the mole fraction. So the total number of moles of water flowing is going to be equal to the mole fraction times the total moles. And the total moles is the flow rate over the average molecular weight. It works out, you can see, I can prove it with units, because you've got, this is going to be moles per meters squared seconds, because the top is kilograms per meters squared seconds over kilograms per mole, and that works out to be that. So like I said, that is the total number of moles of water flowing. And that is going to be equal to the water molecular weight, flow rate over the average molecular weight of the water. So then you can just be rewritten by multiplying this MW over to the other side and say that the flow rate of the water is equal to the mole fraction times the total flow rate over the average molecular weight times the molecular weight of the water. So we've got another little equation to help us solve stuff later. All right, so now we're directly addressing the question of how does the mole fraction of water vapor and air change with position, and that can be solved by creating a mass balance. This is the section where we directly address that mole fraction. The amount of water is increasing in the vapor phase as it goes through the cooling tower, and Kc is that rate that vapor is changing and adding to the amount of water in the air. So of course we're going to start this equation by writing our change in mole fraction, as that's exactly what we're trying to address here. And then multiplying that again by the total moles, which is this little equation we had up here, which is the mass flow rate per area basis times the area over the mass average, molecular average weight And that is going to be equal to the area per volume, which is that little a, big A, and then change in position. And then multiplying that by the molar flux, which is the same as above, which is that Kc, and then the change in concentration from the interface to the bulk of the water. But now we want to connect back to pressures a little bit. So we know that concentration is equal to pressure over the gas constant times the temperature. So for the water at the interface is equal to the pressure of the water vapor, wrong word, I wrote down, at the temperature at that position over the gas constant times temperature. And the same thing for the that bulk concentration, that's going to be equal to the mole fraction times the pressure over the gas constant times temperature. And that this multiplication shows that it is just the pressure of that at that moment, where that's at that mole fraction. Now going back to use given values that we were given in the problem, like the Lewis number that we were given, which is 1, that given equation that we were given with the Nusselt number can be changed to be used from a heat transfer standpoint, which is when it's in the Nusselt number, Reynolds number, Prandtl number setup, to a mass transfer setup, because Nusselt to Sherwood number is that heat transfer to mass transfer analogy. So this can just be rewritten as Sherwood number is equal to 0.6 Reynolds number to the 1/2 times the Schmidt number to the 1/3. Now, looking at the formula for the Lewis number, which we were given as being equal to 1, is actually equal to the Schmidt number over the Prandtl number. And that can again be broken down into the kinematic viscosity over the diffusion coefficient, which is density times the over the kinematic viscosity over the thermal diffusivity. There we go. Which is just equal to the bottom is just equal to the thermal conductivity over the density times the plus the heat capacity times the heat capacity. Now we have some literature values that we can plug into this. We've got the mass transfer coefficient of air is being equal to 0.03 joules per meters Kelvin. We've got the density of air is being 1.2 kilogram per meters cubed. The diffusion coefficient of air in water being equal to 3 times 10 to the negative 5th meters squared per second. And the heat capacity of air being approximately equal to 1,000 joules per kilogram. So using that and these kind of relationships we said above, we know that the Lewis number of air is 1 as given in the problem. So the Sherwood number over Nusselt number is equal to the mass transfer coefficient by some scale dimension, which we're going to call D. It's going to cancel out, so it doesn't really matter, over the diffusion coefficient of air in water. And that's going to be over the heat transfer coefficient times that scale dimension D over the thermal conductivity. And that's going to be equal to the Schmidt number over the Prandtl number to the 1/3. And I'm just going to rewrite this statement again, just down here. Okay, C, D over the diffusion coefficient times the thermal conductivity over heat transfer coefficient, again, times that scale. Here you can see those scales cross out, and that is equal to Schmidt number over the Prandtl number to the 1/3 And then rewriting that again, you can just say that this is all equal to the Lewis number to the 1/3. Now this right here is actually equal to the Lewis number times density times the heat capacity. Then rewriting that Kc over H. And that's equal to the Lewis number to the 1/3. So we can move that Lewis number to the other side. Move that over there. And now we have, and the H, so it's not in the denominator. Heat capacity. You have Lewis number to the -2/3. And as given in the problem statement, we know that this is just equal to 1. So basically, this breaks down even more, and we just have the heat transfer coefficient being equal to the mass transfer coefficient times the density times the heat capacity. And this can be plugged into our equations earlier as a rearranged version, which is the mass transfer coefficient is being equal to the heat transfer coefficient over density times heat capacity. And we know this, and we can find literature values and have other information. So this is a very wonderful simplification now that we have of having this equation. And now we have our differential equations to plug into Python and use. We've got our water, we've got our air, and then we've got our relationships between mole fractions.